So in this video, we're continuing on with section 3.2. And now that we've introduced both properties, open and closed, we want to talk about what the relationship is between them. Now we know that just because a set isn't open, that doesn't necessarily mean that it has to be closed. And just because a set isn't closed doesn't mean it has to be open. Our prototypical example of that would be a half open interval. So looking at, for example, what I wrote down, 0 is included and 1 is not. The fact that 0 is included means that it's not going to be open because 0 won't be able to have an epsilon neighborhood contained entirely in that interval. And the fact that 1 is excluded means that it's not going to be closed. And that's because I can construct a sequence of values that converge to 1, but 1's not in my set. So open and closed they're not like negations of one another. Not open doesn't mean closed. Not closed doesn't mean open. But there is a relationship between them, and we're going to start exploring what that looks like. So the first thing that I want to do is talk about the boundary of a set. Now in your homework, you're going to be exploring the definition of what it means to be a boundary point of a set and what the boundary of a set is. And if we think about like our understanding of open and closed intervals, we've always thought of it in terms of, do they contain their endpoints or not? Open intervals don't contain their endpoints. Closed intervals do. But how do I extend that to general sets that aren't necessarily intervals? And that has to do with talking about whether or not the boundary of a set is included in the set or completely excluded. So the high level here, you're going to use the actual precise definition of a boundary in your homework. But the high level that I want you to think about when you think of boundary is it's essentially the place where you transition between A and A complement and vice versa. So if you were walking down a number line and you were in the set and you stepped out of the set, that means you're crossing a boundary point. Or if you're out of the set and you step into the set, you're crossing a boundary point. Okay, so high level here is the boundary of a set is the collection of points where you transition from A to A complement or vice versa as you walk down the number line. And so what you're going to prove in your homework is that open sets do not contain any boundary points. And closed sets contain their boundary points. So to see how open and closed are actually related to one another, we want to think about how the boundary of a set A is related to the boundary of its complement. So, question. What is the relationship between the boundary of A, which I'm just going to write boundary of A like this, and the boundary of a complement. Well, we just got done saying that the boundary of A is where you transition from A to A complement and vice versa. So if I wanted to extend that definition to talk about the boundary of A complement, since the complement of A complement is just A, we are really saying the same thing. The boundary of A complement is just where you transition from A complement to A and vice versa. So turns out they're the same. I like to sort of think of this in terms of, two houses, two neighbors, and there's a fence between them. One of the neighbors owns the fence, probably, but the fence is still a boundary between both houses. So if A contains its boundary, what can you say about A complement? Well, we just got done saying that the boundary of A and the boundary of A complement are the same. So if the boundary of A is entirely inside A, so I'm going to abbreviate this BD of A, it's completely inside A. But that implies that the boundary of A complement is completely a subset of A. And what that tells us is that if I look at the boundary of A complement and I intersect it with A complement, I should get the empty set. If the boundary of A is entirely inside of A, then A complement shouldn't contain a single boundary point, since the boundary of A and A complement are the same. So A complement will exclude all of its boundary points. So think about what we just got done saying about what we expect with open and closed. Let's scroll back up. Open sets don't contain any of their boundary points, and closed sets contain their boundary points. And we've just discovered that there's this relationship between the boundary of A and the boundary of A complement that's sort of complementary in terms of thinking about open versus closed. So that gives us the following theorem. If you take a set A and R, this set is closed if and only if A complement is open. That's like saying high level that a set contains its boundary if and only if the complement doesn't contain any of its boundary points. So this is what we're going to try to prove. So we have two directions that need to be proven here. And just looking at this logically and trying to think about how we're going to do our argument, remember that it's easier to work with the condition not closed, for example, because that means that you get this convergent sequence, this tangible convergent sequence that you get to use that converges to a limit outside the set. So it gives you something to work with. And similarly, when we know that a set is not open, we get a specific point in our set that has no epsilon neighborhood that stays in that set. And that intuition tells us that perhaps we want to work with the contrapositive when we're trying to prove each of the directions of this claim, because that will allow us to have assumptions like not closed or not open, and that'll give us something to work with. So let's take a look at the forward direction first. And the first thing I want to do is just write out what the contrapositive is of the forward direction. So the contrapositive of the forward direction is just if a complement is not open, then A is not closed. So what I'm trying to do here is, remember, we're focusing on the conclusion. I'm trying to demonstrate that A is not closed, which means I need to come up with a sequence of values, x sub n, that are in A, whose limit is not in A. So I'm looking for this convergent sequence of points from A that converges outside of the set. So we need to show there exists an xn contained in A such that xn converges to X, where X is not a member of the set A. Now, since we are talking about complements right now, it's worth pointing out that when you say that X is not in A, another way of saying that is that X is in a complement. So that's our goal, which means we need a candidate for what that X value is. When you identify that a set is not closed, your goal is to figure out what's that boundary point, that I can construct a sequence that's going to converge to. So the first thing I need to do here is ask the question, what should X be? How am I going to get it? I need to produce this X. So we go and we look at our assumption. And our assumption says that a complement is not open. So we know a complement is not open. And if I write out what that means, it means there exists some X in a complement, i.e. X not in A, that sounds good, such that for all epsilon greater than 0, V epsilon of X is not a subset of a complement. So we need to think about what that means here. What does it mean for the epsilon neighborhood not to be a subset of a complement? Just thinking about the definition of subsets, when A is not a subset of B, for example, it means that you can find a point in A that's not in B. So translating this tells me that each V epsilon of X contains a point that's not in a complement. And if that point is not in a complement, the only place it can be is in A. This is going to be how we construct our sequence. So we will construct a sequence of points in A such that that sequence xn converges to our X. And xn will be comprised of the points in V epsilon of X intersect A. for a sort of a descending sequence of epsilon values. So we're going to look at epsilon going to 0. So let me draw a picture because there's kind of a lot going on here. So right now I have my x. And we were just told that if you put a neighborhood around x, there always has to be some point in there that's a member of the set capital A. So here I have fixed a specific epsilon value. So I could think of this as like x plus my first value, epsilon 1, x minus that first epsilon value, epsilon 1. And from there, I get this point, call it x1. It's in A, and it's in the epsilon 1 neighborhood. So that's going to be the first point in my sequence. And then what I'm going to do is I'm going to choose a smaller value of epsilon. And this one is going to be some epsilon 2. And for that epsilon value, since I know that I also have to have a point in A that's contained in that, because remember we said every epsilon neighborhood of X has points in A. So pick one, call it X2. And then we can just keep descending in size, picking points. And these points don't necessarily have to form a monotonic sequence or anything like that. My point could be over here, for example. That's still decreasing, but then I could bounce to the other side the next time. But I got an X3 in A. So what we need to do is come up with a descending sequence of epsilons, and for each of those epsilon neighborhoods, choose a point that we know exists in A based on our assumption to put in our sequence. And then the fact that we have, since these epsilon n's are going to go to 0, the x n's that we're picking here are going to have to converge to x. And in this way, we have found an xn that is contained in A with x in A complement. And that's going to be how we show that our set is not closed. So therefore, A will not be closed. So let's write a proof of this. So we're doing a proof of the forward direction of this proof. This is by contrapositive. And so our assumption is that A complement is not open. So there has to exist an X in A complement, i.e. X not in A, such that for all epsilon greater than 0, V epsilon of X is not a subset of A complement, i.e. there has to exist a little a that's in V epsilon of X and also in A. So since it's also in A, we're using intersection to denote that. So we're going to consider epsilon n equals 1 over n for each little n in the natural numbers. The reason why I'm choosing this is because remember we said that our argument hinged on choosing a sequence of epsilons that went to 0, which means we have a choice here. Because remember, we get to assume that something works for all epsilon. And if it works for all epsilon, we can specify which ones we're using in a way such that as we pick the point in the epsilon neighborhood, we're constructing a sequence that is forced to converge toward x. The reason it is forced to converge toward x is because of the fact that the epsilon sequence is going to 0, meaning you're getting closer and closer to x. So then by assumption here, there has to exist an xn that's in V epsilon n of x intersect A. Thus, we have xn contained in A. However, since epsilon n as a sequence is going to 0, we are essentially squeezing our values x sub n toward x. You can think of this as the squeeze theorem if it helps. I'm not going to require you to write the proof, but this construction that I'm demonstrating to you is a type of construction that you should be able to do. Whenever you know something is true for all epsilon, you can always choose descending values of epsilon to get closer and closer. We've seen this before when we were trying to construct a sequence of rational numbers that converge to some real number x, and we just used descending sequences of like we used 1 over n and density in order to get that point. In this case, I'm getting the point from my assumption that I'm not open. So since x is not in A is not closed by definition, because we found a sequence in A that converges to a point that's not in A. So we've proven the forward direction using contrapositive. So now we need to prove the backward direction. And the backward direction says that if A complement is open, then A is closed. But again, remember we said that when we work with not open and not closed, that gives us something tangible to work with because we get to make assumptions about things that exist. And we don't have to prove something for all. So here I've written out the contrapositive of the backwards direction. And that says that if A is not closed, then A complement is not open. So we want to focus on the conclusion and make sure we understand that first before we think about what it means for A to not be closed, because it may not be immediately clear how that's a useful assumption. So we are trying to show that the complement of A is not open, which means we need to find an x in A complement such that for all epsilon greater than 0, V epsilon of x is not a subset of A complement. And really, again, what we're saying here is that every V epsilon of x contains a point in A. And just as in the proof of the forward direction, the next question that we want to ask is, what's x? So we now know that we're looking for an x, and then once we find that x, we're going to illustrate that every epsilon neighborhood leaves A complement. In particular, that means it contains a point in A. So what's x? That means we need to take a look at our assumption here. We know that we're not closed. And so remember what that means. We know that there has to be a sequence. Now, the set that's not closed here is A, so that's telling us the sequence lives in A, such that xn converges to x, but x is not in A. And remember what that means. That means X is not in a complement. And so now notice we have what we wanted. We were looking for an X in a complement, and we just got, oops, I have a mistake. Sorry. We're going to say in here. So the point I'm trying to make is that we were looking for an X in a complement, and that's exactly what we get from looking at the definition of not closed. So then we just have to understand what it is, why is it that because Xn is converging to X, that every epsilon neighborhood has to contain a point in A. So let's take a look. So we're asking the question, why does every V epsilon of X contain a point in A? Well, let's look at our picture. We have our X. We know that X, remember, is in A complement. But we just said we have a sequence of values that is converging to X. And those values are each coming from A. So maybe I have something like this. So let's say that's X1, X2, etc. So I'm trying to understand, if I pick an arbitrary neighborhood, an arbitrary epsilon neighborhood of X, why does it have to contain a point in A? Well, look at it. The entire tail of the sequence has to be in that neighborhood based on convergence. And if the entire tail has to be in that neighborhood, then certainly there's at least one point from the sequence in the neighborhood, in particular, X of capital N. And that's all we needed. So since the tail of Xn is in V epsilon of X, and since Xn is a subset of A, any point in the tail can be used to show that the epsilon neighborhood of X isn't contained in the complement. That's because each Xn is in A, but also in the epsilon neighborhood when you're talking about the tail values. So let's write the proof, because we now have the construction here. Remember, our goal was to be able to find what our X is. The X had to be in the complement, and then we wanted to demonstrate that every epsilon neighborhood of that X was not a subset of A complement. That's the way that we prove that A complement is not open. So this is a proof of the backwards direction. And again, this is by contrapositive. So I get to assume A is not closed. So just using the definition, we said that means there has to be this sequence Xn contained in A such that Xn converges to X, where X is not in A. That is, X is in A complement. Now I'm going to argue that for all epsilon, V epsilon is not a subset of A complement. That means I need to introduce an arbitrary epsilon. So I'm going to let epsilon be greater than 0. And our goal now is to argue that I can find a point in the epsilon neighborhood that's also in A. So I'm going to use the definition of convergence here. Since xn is converging to x, there has to exist a capital N in the natural numbers, such that for all little n greater than or equal to capital N, xn is a member of V epsilon of x. So in particular, x sub capital N is in V epsilon of x. And since we said this is a sequence of points from A, it also has to be in A. This proves that V epsilon of x can't be a subset of A complement, since it contains, when I say it here, I mean V epsilon, contains a point in A. By definition, A complement is not open, since this was for an arbitrary epsilon value. The last thing that I want to talk about is has to do with what we can say about collections of closed sets. If I take the union of closed sets, does it have to be closed? If I take the intersection of closed sets, does it have to be closed? And if so, how many sets can I union, or how many sets can I intersect and still get that result? So here I've written out a result that we proved way back in one of our beginning lectures for this section. We showed that the union of an arbitrary collection of open sets is open, and that the intersection of finitely many open sets is open. Recall that when I say arbitrary collection here, I'm including the case where I actually have infinitely many open sets that I'm looking at. But we also now have this theorem that we just wrote out. We said that A is closed if and only if A complement is open. So if I want to be thinking about collections of closed sets instead, say I have AN closed. We now know that that means that AN complement is open. And we know what happens with open sets. So let's say I wanted to figure out the union of AN. Is the union of my ANs closed? That's what I would like to know. Another way I could ask that, equivalently, I could ask, is the complement of the union open? And so here I'm talking about the complement of the union of sets. This should ring a bell for you. This is, we can use De Morgan's laws. I think it might actually be an A. So we can use De Morgan's laws. So if I take the union of the ANs and I look at its complement, using De Morgan's laws, that is the intersection of each of the individual complements of the ANs. And we know something about this, remember? We know that that is open. We know that AN complement is open. So it turns out that talking about a union of closed sets comes down to talking about an intersection of open sets. And we know that this will be open as long as the intersection is finite. And so that's like saying that if you want to understand whether or not the union of sets are closed, which again we said that means the complement of the union has to be open, talking about the union of closed sets is related to talking about the intersection of open sets. So that's what we just found here. The union of closed sets is related to the intersection of open sets. And we can make a similar statement if I wanted to ask the question, is the intersection of A sub n closed? Then that would be related to the union of open sets. So what we see is this result that we have up here for open sets. We're going to get an analogous result for closed sets, except it's going to be switched. It's going to be the intersection of an arbitrary collection of closed sets is closed, and the and the union of finitely many open sets is open. So I'm not going to write out the full proof of this. We just proved the case where you look at the union of closed sets. I'm not going to write out the case for the intersection of closed sets because it's analogous using De Morgan's laws, but I am going to write down the theorem. So we said that the intersection of an arbitrary collection of closed sets is closed. And the union of an arbitrary collection, of finitely many, I got carried away, of finitely many closed sets is closed. To see why it matters, why you can't necessarily have an infinite union of closed sets guaranteed to be closed, let's give an example of an infinite union of closed sets that's not closed. And one of the simplest types of closed sets is just a set that contains a single point. So given X in R, the set of just X is closed. Well, let's think about this. Definition of closed is given any sequence of points from inside your set, you need to prove that it converges to a value inside the set. So consider any xn that's contained in my set of just X. Well, the only type of sequence that you can generate from this set is a constant sequence of just X itself, because you only have one choice for what point you put in the sequence. So this converges to X, which is certainly in X, in the set X. So now I'm going to be clever. Recall Q is countable. And remember what that means. It means that we can write out, we can enumerate its elements. So if I wanted to write Q, I could think of it as the union from n equals 1 to infinity of these sets that contain just one of the values that I've listed. So these two sets are the same. Take every an, put them all together, I have all of Q. But according to our claim that we just showed, we know that these individual single point sets have to be closed. And what you'll show for homework is that Q is not closed. And the key here has to do with the fact that Q is dense in R.